So in our homework packet, using this curve, as we're told in problem 1, we're given percent saturation. What y-axis are we not given? Oxygen carrying capacity. Sometimes it's oxygen content, which is not the same thing. Close, but not identical. Oxygen carrying capacity refers to your hemoglobin grams percent times 1.34 mil O2 per gram. Do you remember that? Oxygen content, if you look at your last lecture, oxygen content is where we add the amount of oxygen dissolved in your plasma according to Henry's law, which under normal conditions is 0.3 milliliters per 100 milliliters of plasma, plus your oxygen carrying capacity. And that's usually, if it's 15 grams percent, it's usually 20.1. So oxygen carrying capacity is not identical to oxygen content, but it's close, because the amount of oxygen we transport dissolved in our blood is pretty low, almost negligible. And I told you that we would need an astronomical cardiac output if that's all we had was the amount of oxygen dissolved in our plasma to deliver to our tissues. It would not be compatible with life. So we're not given that extra y-axis like we saw with the problem set we just did. And with that, we didn't need a calculator, did we? We could calculate, we could see on that y-axis how much oxygen carrying capacity Charles had and how much he could drop off with any pressure change. That is not the case here. You actually have to use good old-fashioned math. So the first problem, you're told that this patient has a hemoglobin grams percent of 15. So if I have a hemoglobin grams percent of 15, the first thing I'm going to do is calculate his oxygen carrying capacity, which would come out to 20.1. Agreed? Okay. Then it says, we want to know, determine the amount of oxygen released from hemoglobin alone. I don't need to worry about the dissolved because we're only focusing on oxygen carrying capacity, and that's okay because this is negligible anyway. How much will be dropped off if we go from a PO2 of 100 down to 40? How much will be dropped off? In the Charles example, that was question number 5. We went from a PO2 of 100 down to 20, and we saw that he went from 10 down to 7.5, which meant he dropped off 2.5 milliliters of oxygen for every 100 milliliters of blood. Do you remember that? Well, the question is, how do we calculate this using this graph that we were told to use here? And I'm going to show you where it was. Ready? I'm going to back up. How much oxygen is released to the tissues for each 100 milliliters of blood? Do you see that? Okay. So it says use this graph, and we're going to go from a PO2 of 100 to 40. It's the same question. And you see down here, I went up at 100, I went up at 40, and I went over to my percent saturation. Why did I use percent saturation? Well, because this other y-axis on the curve we're supposed to use isn't given to us, is it? We'll come back down here. Nope, it's not given to us. And this is a right-shifted curve. So if you thought you could use that same picture, that's normal conditions. That's not hypercapnic acidotic. So you couldn't even use that even if you wanted to. So what do we see? We have to, I'm trying to get it to a spot. What do we have to do? Take the percent saturation at 100 and subtract from it the percent saturation at 40. Turn that into a decimal point. So that's 0.975 minus 0.75. Then multiply that by your oxygen carrying capacity, and you'll find out how much oxygen you dropped off in the tissue bed. This requires your calculator. The Charles example, we didn't need it because we were given a second y-axis. We will all get slightly different answers for number 1 because it all depends on how well you draw your straight line going over to the percent saturation axis. If it's slanted, you're going to get slightly different percentages, and it also depends on what percentage you think you're intersecting at. It's going to be somewhat subjective. But you should get in a general range. So what'd you get?
6.7 minus 6.5.
Let's do this together. We have to go up from 100, up, hit, go across. What do you want to call that? 97? That's 97.5. So what do you want to call it? What's that one? 80?
Yeah.
90? Sure. Okay, and then we're told 40. We go up, 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 and across, cross, 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 cross. What do you want to call that?
58.
I'm going to go with 50. So then I take my 20.1 times 0.4, because that's the difference between 0.9 and 0.5. And that tells me how many milliliters of oxygen is dropped off to this person's tissues. Again, depending on how you drew your line and what percentage you thought we intersected at, you might get a slightly different value. That's okay. Did you get around 8-ish? Plus or minus 0.5-ish on either side? Good? Relatively? Who's with me? You're all comatose. 8 milliliters. Okay, so then problem 2, we want to know how much oxygen is released when we go down to, so now he has an arterial blood of not 100, but 70. And then a venous blood of 25. He has the same hemoglobin grams percent. I'm not using units just to expedite things, but naked numbers are bad numbers, just so we're clear. Do as I say, not as I do. So what do you want to call this? 80? What do you want to call that one? Sure, 25. Did you get 11-ish, plus or minus 0.5 on either side-ish? Close-ish? Can you do number 3? The same technique, except that patient has a different hemoglobin grams percent, so you got to start over a little bit.